This is lecture 4G4 for Calculus 1 on maximizing profit. This is another example of using the first and second derivatives to find a local maximum or local minimum along a curve, and thereby maximizing either profit or minimizing cost. In this case, we'll be maximizing profit. So this is a revenue and cost equation problem. We have a revenue that looks like this, minus 0.4x squared, probably from some discounting scheme, plus $108 times x. X will be the number of items we sell. The 108 is approximately the cost that you would, or the price you can be charging for these items. The second equation is a cost equation, and it contains a fixed cost of $2,000. That would be your rent, any manager's salary that you pay, and then you make the items, well, roughly for $8 each, selling them for 108. That looks pretty good, right? But then you have another term here, say 0.6 times x squared, due to perhaps some inefficiency in your manufacturing process. So the more you try to make, the more that gets broken or something happens to them. Perhaps your workers are inefficient and your costs go up. So the more you try to make, the more it costs you to make them. But the base price is like $8 each. You're selling them for $108, but you're a little wishy-washy on that because you'll discount. See the minus 0.4, you'll discount for large orders. So given these two equations, you'd like to maximize a profit. How many should I plan on selling, or how many do I have to sell, say per month? These were monthly costs and monthly revenue. How many do I have to sell per month in order to maximize my profit? All right, so first you determine the profit, and profit is revenue minus cost. Oops, sorry, I didn't hear revenue minus cost. So making that subtraction, you get that the profit is minus x squared plus 100x minus 2,000. All right. From this, you could solve this problem with algebra very easily, and in 107, you might have done it already. This is a parabola that is opening downward, since the coefficient of x squared is minus 1. So what you're looking for is the vertex, and right now you know that you're looking for a maximum, and that there would be a maximum when you find the vertex because the parabola is opening downward. But we're going to go ahead and use this as an exercise for calculus and solve it using the first and second derivatives. So the first thing I do is take the derivative, and the derivative is minus 2x plus 100. At a critical point, this is called the marginal profit anyway when you take these derivatives, marginal cost, marginal profit, and marginal revenue when you take the derivative with respect to x, with respect to the number sold or manufactured. So here we've got the marginal profit. When the marginal profit is 0, you are, in this case, at a maximum, but at any rate, you're at a critical point. Just from doing calculus at this point, we do not know if you're at a maximum or a minimum. There is one endpoint to consider, since the domain is closed at 0. Infinity, of course, isn't going to help us out much, but 0. So let's look at 0. At x equals 0, the profit is minus 2,000. We sincerely hope that is not our maximum profit. So let's continue and look at the second derivative. So I'm going to take the second derivative, and when I do that, I find that it's just minus 2. That means the second derivative is constant, all right, for all values of x, including the critical point. If the second derivative is negative, the curve of the function, in this case the profit, is concave downward. That critical point is a local maximum. This just verifies what we sort of knew from algebra, but we want to go through the exercise anyway. You have a function, you take the first derivative, you find the critical points. You evaluate the critical point by looking at the second derivative. It will tell you if it's a local maximum or a local minimum. Of course, there's all kinds of pathology around, but these are continuous functions, and this is basically what you're doing. Okay, so that says that my critical point, which was x of 50, is my maximum, and if I put that back in the equation, the maximum profit I'm going to make is $500 or $500 million zillion dollars, depending on your business, when I have manufactured and sold 50 items. Let's look at those derivatives. So the blue line was the first derivative. To find the critical point, you find where it crossed the x-axis. You find where it was 0. It is 0 when x is 50. Okay, now you don't know whether that will translate into a local maximum or local minimum, so you look at the second derivative. The second derivative is minus 2, right? So it is negative at the critical point, which lets us know that that critical point is a local maximum. And here's a graph of the profit for this business. It does start off at minus 2,000, which was the fixed cost. So your profit always starts out at the negative, the fixed cost. Because you have this quadratic function, you actually have two break-even points. Here was one of them right here. Here's another. Actually, we could have solved for those, but we didn't. What we were looking for is the maximum. The maximum here is at 50. Okay, with the maximum profit of 500.